where we're at, we talked about a little bit about spectral things. We have these linear transformations. There are these things called eigenvalues and eigenvectors. Then we talked about graphs. We said, oh, well, you know, graphs are about connections. And then you can draw little pictures and dots and lines. And, well, we care about, you know, is this next to that? How far apart are things? And when you think about these two things, you're like, well, are they connected? Maybe. But it's not so clear. So we'll start by talking about the adjacency matrix, and I really do mean matrix here. Last time we talked about the incidence matrix, but when we were using the incidence matrix, we were just using it as an array. And so here we really want to start talking about like matrix type things. And so the goal is, what do we have? Well, we're given a graph. So given our graph G, we associate it with a matrix. And so, well, this is the natural matrix in some sense. And if you walk down the street and just mention to somebody, hey, I'm studying spectral graph theory, they'll say, oh, you mean the adjacency matrix? You know, of course, because everybody you'll meet knows spectral graph theory. You know, such a great subject. So the way we construct this matrix is we're going to index the rows and the columns by vertices. So everything's indexed by vertices. And now we look at an entry. And this entry is going to be one of two things. Namely, it's 1 if, and I should label some vertices here. So U and V. So U for the row, V for the column. And maybe I should get a darker color here. Let's try again. There we go. U and V. And the point here is 1 if U is adjacent to V, and we use a little squiggle line as a shorthand for adjacent, and 0 if it's not. And that's it. So it's a 0-1 matrix. On, off. Are you adjacent? Are you not adjacent? So, all right, that seems pretty clear. And in some sense, it's the simplicity is one of the reasons why this is the first matrix that people considered. And so we'll start with a classic in graph theory. This is a graph called the PAW graph. And, well, all small graphs have names. So this one is called the PAW. And the idea is this part is the paw, and then here you have the arm. All right. So if I'm going to associate this with an adjacency matrix, the first thing I have to do is I have to actually pick vertices. I have to label. So, okay, 1, 2, 3, 4. And now, well, I see 1 is adjacent to everything, but not itself, since there's no loops. So it'll be 0, 1, 1, 1. 2 is adjacent to 1 and 3. So 1, 0, 1, 0. 3 is adjacent to 1 and 2. 1, 1, 0, 0. And 4 is only adjacent to 1. All right. And there we go. Okay, so that's the PAW graph and the adjacency matrix for the PAW graph. Well, actually it's not the adjacency matrix for a PAW graph. It's the adjacency matrix for that particular labeling of the PAW graph. And you might ask a question, well, what would happen if you choose a different label? Can you? Well, sure. Why not? I can do that. I could put vertex 1 here, vertex 2 here, and 3 and 4 at the top. And of course, what would that produce? Well, in that case, 1 is only adjacent to 2. 2, well, it's adjacent to everything but not itself. And let's see, 3 is adjacent to 2 and to 4. And 4 is adjacent to 2 and 3. And so you'd end up with that. And of course, different labelings will result in different matrices. So you see, okay, so in some sense, the adjacency matrix is not unique. There's a choice. The labeling you pick will determine what kind of matrix you get. Now, that's a problem, but the question, does the labeling matter? Well, of course, the answer is maybe, depending upon what you want. And so we'll be a little bit more precise in asking this question. Does the labeling matter as far as eigenvalues are concerned? So in other words, if I change my labeling, which changes the matrix, do I also change my eigenvalues?
No.
Should be no. Okay, so you change eigenvectors, but you change them in kind of a very predictable way. Well, you permute things around. So can we explain why it doesn't change? Can anyone say, aha, it doesn't change because blah, blah, blah?
Because all you're doing is you're conjugate, or these two matrices are permutation similar. You can get a permutation matrix on the left and then take its transpose and hit it on the right. And we know that similar matrices have the same eigenvalues. We can prove that pretty easily. But
right.
That's our
Matrices are nice.
Right. Well, of course, that's, permutation matrices. We can just explain this in the underlying notion of what matrices are, right? They're linear transformations. When we do this kind of permutation, which is what we're describing here, all we're doing is really we're just permuting our basis. Because we think of our basis elements, we have, in this case, 4 basis elements, and we're just permuting which one is which. But the linear transformation doesn't depend on the basis, and the eigenvalues are tied to the linear transformation. Yeah, and it is a similarity argument, as you say. So they are permutation similar. And so good. So that makes us happy. And in particular, okay, the answer we'll write down, no. So this says that when we talk about the spectrum, it's the spectrum associated with the adjacency matrix. And, or well, I guess technically we should say it's the spectrum associated with an adjacency matrix, but it doesn't matter which labeling we choose. Labeling independence. This is like an important thing in graph theory, at least in my opinion it is. Anything which is labeling dependent tends to be uninteresting because it's not capturing what a graph is. A graph is about connections. How are things connected one to another? And so when you start saying, oh, the labeling matters, then you start losing that. And so the fact that it doesn't matter, life is good. Life is wonderful. All right, so now that we've done this, I want to go through and talk about some of the various graphs that we've encountered and try to see, all right, let's see if we can figure out some of the eigenvalues associated with them. So let's start with perhaps the easiest graph. All right, so the empty graph. And you probably were thinking of a different graph, but no, this one's definitely easier. So the empty graph on n vertices. Now what is that? Well, you just have n dots, right? That's the empty graph. So what's the adjacency matrix look like? Yeah, it's the zero matrix, represented by a capital letter O oftentimes. But, all right, the zero matrix, so good. And in this case, no matter how you permute, it's still the zero matrix. And, all right, so what are the eigenvalues? Yeah, good. Okay, so we've successfully have been able to find the eigenvalues associated with a graph. All right, good. We've done spectral graph theory now. We've checked that box for the semester. But we'll do more. We'll do more. All right. Anyone have another favorite graph that they like?
Cycle.
Oh, okay. Sure. Sure. We can go there. The cycle graph. Okay, the cycle graph. Now, this will be a little bit longer than the empty graph. But we'll get there. We'll get there. If not today, by next time. We'll get there today. We'll get there today. Okay, so before we get all the way into the cycle graph, we're going to sort of take a step back and jump around a little bit to talk about things that we need to know. So let's start with a particular matrix. Okay, so this is coming soon. I don't think we'll be able to fit it on this page. So the first matrix I want to talk about is the following matrix, and namely, I'll start writing it down. And so it looks like the following. And here's the key, is that when you look at this matrix, it has a single band of ones sort of on the super diagonal plus a little tiny one in that bottom corner. Okay, so this is our matrix that we're looking at. Now, we could think about this as a matrix for a graph, but in this case, it has no symmetry. It's not symmetric. But that's okay, because you can talk about adjacency matrix for directed graphs. So if you were to think about it in this way, well, you could think of it as saying, well, suppose I have my vertices 1, 2, up to n, and then I have directed. So I could say 1, 2 is a pair. So 1 goes to 2. 2, 3 is a pair. And then you just sort of work your way around. And so it's sort of like a directed cycle, is how you could see it. All right. So now I'm going to claim that this particular matrix has nice eigenvalues and eigenvectors. And the reason I can claim that is we can write them down. Okay, so let's look at omega, which is going to be an nth root of unity. So, in other words, omega to the n is 1. That's what I mean by an nth root of unity. Now, I want to take this matrix, and we'll just fill in a bunch of zeros here, and I'm going to multiply by 1 omega squared down to omega to the n minus 1. What does this give us? So we can carry out the multiplication, right? So on the first row, what would you get? 0 plus omega plus a bunch of zeros. So the first row would be omega. I should say the first entry should be omega. It's a vector, so I suppose I'm technically not right by saying the first row. The first row of this vector, also known as the first entry. What's the second entry going to be? Omega squared. The next entry? Omega cubed. And essentially what's happening is you can think of as you're handing off the values. And because that's what it is. That's actually what's happening. Okay, down to at the very bottom, well, at the penultimate one, that's a very fun word to say, it's omega n minus 1. And then what's the last one? 1. Because I'm passing this value on. Okay, good. I'm wondering if I got my arrows right. Well, close enough. Okay, so, but what's another way to say 1? Omega to the n. Aha. Now, I say, well, look, all of these have omega in them, so I can pull that omega out. So that's omega 1, omega squared, down to omega to the n minus 1. Yes? Now, good news. We have matching. Okay, so when we multiplied this matrix by this vector, I had, lo and behold, the same matrix with this value omega. All right, so now a great aha. This says omega is an eigenvalue. And we also know the eigenvector. So the eigenvector looks like 1 omega squared down to the omega n minus 1. Okay. Good. And now we can pause for a second and ask some questions. We found n eigenvalue. Well, actually, how many eigenvalues have we found? Why do you say n?
I'm thinking.
Well, it is for any nth root of unity.
Well, how many nth roots of unity are there? There are n nth roots of unity. And each one of them is going to be an eigenvalue. Okay, so how many eigenvalues are left for us to find? None of them. Because we have them all. Because we know that an n by n matrix has at most n eigenvalues. At least we believe that. You know, I'm sure there's a theorem in linear algebra that says that. But essentially, if we haven't talked about characteristic polynomials, but characteristic polynomials are, it's the degree of the matrix is the size of the matrix, and that's the number of possible roots. Okay, so good news, we have our eigenvalues, we have our eigenvectors. Okay, so let's now cycle graph continued. We're going to talk about another notion. And the next notion that we will need as we build up to the cycle is the notion of a circulant matrix. And with that, we can even talk about circulant graphs. So a circulant matrix. Does anybody know what a circulant matrix is? All right, cool.
Isn't each row the same but like shifted one?
Yes.
Okay.
Yes, that's the example. Okay, so we'll basically the idea here is you start. Let's do. I'll do 5 by 5. So the circulant matrix is set up so that once you know the first row, you know everything. And the idea is you copy the first row except you move over. So C0, C1, C2, C3, C4. And then you shift it over again. C0, C1, C2, C3, C4. And so what's happening is that when you look at these values, what you see is the C0s, they form a diagonal. But really any CI forms a diagonal. So if I pick, say, the C2s, well, those also form a nice diagonal. Now, what we have is that we have really the nice following observation is that we now know how to do a really special case of a circulant matrix. Namely, if I look at this circulant matrix, where the C1 is 1 and the rest of them are 0. Okay, we know how to do this one. So this we're happy with. All right, this is mathematical notation, by the way. Okay, so we're happy with this one. Now, let me ask a slightly different question. Suppose I were not to have the circulant matrix where I know C1 is 1 and the rest are 0, but suppose I look at something where, I don't know, let's say this is in the kth entry here, But then I go down to 1 and I wrap around as before. So essentially it's the circulant matrix where now it's the CK is 1. Can we do this one?
Yes.
Now, usually when I ask that, the answer will be yes. So that's a good sign. You're picking up on this. How do we do this? What powers? Right. So if we call this matrix something, call it U for a moment, then this matrix we can think of as being U to the power K. All right. Now, we said we were happy with this one because we know what the eigenvalues are. Do we know what the eigenvalues are for U to the K? Okay, someone's saying yes. What are they?
It's the same. But
The kth power.
it's the eigenvalues of U to the K power, but it'll just give you the same eigenvalues.
Right. So it's omega to the K. Now, it may or may not be the same eigenvalues. It depends on your, because depending upon your power, you might have some of the roots might sort of land on top of each other. So, for example, if you take omega to the n, they all are on top of each other. And, but of course there are cases where they won't, if you have things like primes, but, the punchline is it's omega to the K. And that's our eigenvalues with the eigenvector, same as before, 1 omega squared down to omega to the n minus 1. Okay, so here's the fun fact. I claim we can write down the eigenvalues for any circulant matrix. It takes almost no work at all. Well, why? Because let's look at this one. Really, I can think of this as C0 u to the 0 plus C1 u to the 1 plus C2 u squared, C3 u cubed, and C3 u to the 4th. C4 u to the 4th, thank you. Now, why is this nice? Well, because they all have the exact same eigenvectors. And so, I can simply multiply this by 1 omega squared down to omega to the n minus 1. And what happens? Well, we end up with C0 omega to the 0 plus C1 omega to the 1, C2 omega squared, C3 omega cubed, plus C4 omega to the 4th, times 1 omega down to omega to the n minus 1. Which means that, lo and behold, these are our eigenvalues. So once you have any circulant matrix, you're basically, you get all the eigenvalues. You just need to know what your entries in your first row are, and you fill that in, and you run through each root of unity. And so for each root of unity, you get an expression. All right, good. Now, we're almost there. We'll get to the cycle graph. Okay, so here we go. What does a cycle graph look like? Well, for a cycle graph, what we have is we have zeros, ones above the diagonal, ones below the diagonal, and then we get ones in the corner. So that's what you get for a cycle, with an appropriate labeling, namely the obvious labeling. 1, 2, 3, up to n, back to 1. So if you choose that labeling, this is your matrix. Well, what kind of matrix is it? It's circulant. Yes. Aha! No surprises. Well, we set it up. Otherwise, that was a really long distraction if it wasn't going to be useful. Okay. So now that we know it's a circulant matrix, we say, okay, well, great. What do we see? Well, what we have is where are our entries at? So here, this entry is in the 1 slot in the first row. So I'm reading off the first row. So the 0 slot is a 0, the 1 slot is a 1, and back here at the end, in the n minus 1 slot is a 1. So the eigenvalues for the cycle, well, they are going to be omega to the 1 plus omega to the n minus 1, where omega to the n is 1. So then we have to run over all the roots of unity. Okay, we can clean some things up. Since omega to the n is 1, what's another way to write omega to the n minus 1? Yeah, so this is the same as omega to the 1 plus omega to the minus 1. All right, let's talk about our nth roots of unity. What do they look like? In terms of e to something.
To the 2 pi I over n.
So e to the 2 pi I over n is an example of an nth root of unity.
Like k for some k.
Right, and then you have k. And then where k goes from 0 up to n minus 1. And that is each of the nth roots of unity. Okay, so we're almost there. Because this somehow doesn't feel right. You might say, why not? Well, the reason it doesn't feel right is we have this sort of underlying idea that we were going to keep things real this semester. We should have real eigenvalues. And these look complex. And so we don't want that. And so the question is, can we make them real? And of course we can. So we say, all right, so let's write down what we have. This is e to the 2 pi I k over n. That's the omega. Then plus e to the minus 2 pi I k over n. Okay, now where are our analysis people who can say, hey, this has a name?
I'm not an analysis person, but I took complex last semester.
Okay,
They're complex conjugates,
right.
so their sum is going to be real.
True that. Yes, but it has a name.
Are these hyperbolic functions?
They're kind of hyperbolic functions. It has the flavor of hyperbolic functions if the i's weren't there.
Is that
2 cosine or 2 hyperbolic?
Yeah, so it's the cosine function. So cosine theta is e to the I theta plus e to the minus I theta over 2. Now we don't have an over 2, which is why we need a 2 cosine. So this, in our case, the theta is 2 pi k over n. So we get cosine of 2 pi k over n. And when this is true, this is for k equals 0 up to n minus 1. So here we have our eigenvalues.
2 times cosine?
Oh yeah, there's a 2 in there. Aha, thank you. See, I left plenty of room for me to put that in there. Thank you. And there we go. Whew, we did it. We still have plenty of time left. Okay, I should warn you, we don't have that many tools, but we still can do a few more. So any other popular ones? Okay. I was thinking people were going to go with complete graph before they went with cycles. But, okay, cool. No. No.
Because after the last lecture, I think.
Well, we'll get to Peterson graph. We'll probably do Peterson graph in a couple of different ways. And all right. I should say that there are other graphs out there which also have circulant matrices as their adjacency matrix. An example of one is the complete graph. That probably, though, should not be like, oh, let me do the complete graph by using tools of circulant matrices. We could do it, but we like ourselves.
Oh, listen, this was a problem on the first exam in linear algebra. Not explicitly the adjacency matrix of the complete graph, but that matrix. And I did implicitly solve it with the circulant solution, and Joey yelled at me for overthinking it. So.
Yeah, but I mean, there are other cases where you may want to do that. I mean, there are things. So we talked about the cycle. So you can talk about the square of the cycle. Are you familiar with what the square of the cycle is?
Is that when you cycled every second vertex?
Yeah. So essentially, if you start with your graph, and which is a cycle, and I just want to put enough vertices in here so it looks interesting. And then the square of the cycle says, oh, also add in edges for vertices which are distance 2 apart. And so that's the square of a cycle. So you can talk about the square of any graph. And could you find these eigenvalues?
Yeah, we just talked about it.
Yeah, it's the circulant matrix. So there's actually a lot of interesting graphs which can be phrased in terms of circulant matrices. But on to the complete graph. Okay, so we could do it by circulant tools, as we mentioned, but we won't. Okay, so the complete graph, we'll draw a quick example. We'll do 5 vertices because that seems to be the tradition with complete graphs. All right, and well, what does the adjacency matrix look like?
All ones minus
Yeah, so on the diagonal, you have zeros, and then off the diagonal, you have ones, because everything's connected to everything else. Now, you mentioned all ones, so there's a nice way to write the all ones matrix, and this will be a matrix we will see a fair amount. So the all ones matrix shows up disproportionately often in spectral graph theory, so we should make sure we're familiar with it. So if you see a capital J, we will be fairly consistent. This is the matrix with all 1 entries. All right. Now, we can do this in a couple of different ways, and let's maybe start by the following. Let's not worry about J minus I. Let's talk about the eigenvalues of J. Just the all ones. So I have here a matrix, and it has all 1 entries. What are some things that we can say about it? Rank 1. Okay. Good. Why do we know it has rank 1? Because all the rows are the same. Yes. And of course, that row is a non-zero row. So rank 1. Now, what does that tell us about the eigenvalues? Yeah, we have to have a lot of zeros. So the eigenvalues are something and 0. All right, we've already, just a rank argument. Okay, now can we find the something? What's the something? It's n. All right, how do we get that?
Multiply by the one vector.
Yeah, so we can explicitly find that eigenvector. And so namely, if you multiply by all ones, what you get, well, is, in this case, it's a 5 by 5, so you get 5 times all ones. In general, you'd get n times all ones. And of course, this is now our first time, I think, that we've mentioned the all ones vector. And so we should pause and say that when it comes to spectral graph theory, the all ones vector, oftentimes denoted using a bold 1, is celebrated. This is sort of like the vector when it comes to spectral graph theory. And we will talk about this vector again and again and again.
You're writing ancient implicitly before.
And
This is a root thing.
yeah, well, so I should pause and say, so why is the all ones vector so important? There's sort of a couple of reasons. And one reason that the all ones vector is so important is because it shows up as an eigenvector for a very nice class of graphs. So suppose I have an adjacency matrix, A, and I multiply it by the all ones, and I have an eigenvalue. For some mysterious reason, I'll call it D times all ones. What does that tell us about the graph? So if all ones is an eigenvector, what must be true?
Like a click or something?
It's deregular. Because what's happening is, if you think about what does it mean to multiply by the all ones matrix, what you're really doing is you're row summing. So multiplying by the all ones says, look at all my row sums. All my row sums are equal, and they're equal to this value D. And so that says the graph is deregular. And so a lot of times when you read papers in spectral graph theory, they'll oftentimes say, we'll assume our graphs are regular. What they're really saying is we're going to be in cheat mode. And that we're going to make sure that the all ones is an eigenvector. It also says we really don't know which matrix is the right matrix for us to use. And so we're going to make it so we actually have every matrix at our disposal. Now, that's vague and maybe not clear about what that means, but in the next few weeks we'll be like, oh yeah, when a graph is regular, if I understand what's happening with one matrix, I essentially understand what's happening with all the common matrices. And so that's why I call it you're working in cheat mode. But you have to start somewhere. Another reason why it's important, and this I'm going to be maybe a little bit more philosophical and not as precise, is because when we think about combinatorics, and we think of graph theory as being part of combinatorics, we oftentimes think about the discrete nature of things. And so we're saying, okay, well, how do we think about the discrete nature of graphs? And one of the things that we look at is we look at subsets of vertices. So in spectral graph theory, we oftentimes are highly interested in, let's say U, a subset of our vertices of our graphs. And what we can think of, and this is really getting, I've gone off on a huge tangent because I now look at wait, aren't we supposed to be doing the eigenvalues of the complete graph, and now we're doing philosophy? But okay, we'll by the end of class, we'll have the eigenvalues of the complete graph. Don't worry. You will not leave today wondering, what is it? What could it possibly be? Don't worry, we'll finish that. But when we think about subsets of vertices, how do we think of it from a linear algebra perspective? And so, how do we think of our vectors from a linear algebra perspective in terms of the graph? So that's a question that we can go back to. Well, we'll draw our PA graph because it's easy to draw. And we say, okay, well, what's going on when I have my matrix here? Well, I did my labeling in the way I probably normally don't do my labeling. So this will throw me off for a second, but that's okay. Okay, I think that's the PA graph. All right, so when I'm thinking about a vector, what's the vector mean in terms of the graph? So I have a vector here, A, B, C, D. Because we think about vectors as interacting with matrices. What does that mean in terms of the graph?
Well, it's weighting the edges. Or it's like putting weights on it.
Well, why do you say edges?
Because the ones are the edges.
Yeah, the ones.
Ones are the edges, but in terms of the vector, look at the size of the vector. Now, of course, this is a really bad example with this question. When you think about the matrix, what are you indexing by? We're indexing by vertices. So the vector should be indexed by vertices. So when I think about this A, B, C, D, what I'm really saying here is I'm assigning values to vertices. So vertex 1 would be an A. I should probably choose a pen that can write sharp. A,
Per edge.
B, C, and D. Now, you mentioned multiplying. What does multiplying by our matrix do? Because, you might say, well, does the adjacency matrix have really any interpretation underneath? So this arrow right here, we could call the adjacency operator. And we're applying this adjacency transformation. What do the entries become? So like this entry down here.
The sum of the entries of their neighbors.
Yeah, it's the sum of the neighbors. So this would be B, this would be A plus C plus D, this would be B plus D, and over here would be B plus C. And so you can think about there's an interpretation in terms of what's going on. Now, the reason I say the all once vector is nice is for any subset, we can look at what we would call 1 sub u, which is an indicator vector. Namely, it's a 0, 1 vector, 0 if you're in U, 0 if you're not in U, 1 if you are in U. And so a lot of things will come down to saying, hey, look at the discrete nature of things. What's happening with these 0, 1 indicator vectors? Okay, now we only have a few minutes left. We really do need to make sure we get the eigenvalues of our complete graph. Okay, we were close though, right? Because we found the eigenvalues of J, and now we're subtracting I. So what happens when you subtract I from a matrix? Okay, so why does it subtract the eigenvalues by 1?
Because, you just do the math. Like if V is an eigenvector, then J minus IV is equal to JV minus V.
Right.
And then JV is lambda V and the V factor.
Right. So J minus IV. So this is a nice thing about the identity. That's J times V minus I times V. And, well, okay, so that's lambda V. Because you assume we started with an eigenvector of J. And minus 1 times V, which becomes lambda minus 1 times V. So in other words, adding or subtracting multiples of the identity, it's really easy to say what happens to your eigenvalues. We know what our eigenvalues of J are, and so the eigenvalues of J minus I, well, that will be n minus 1 and a lot of minus 1s. And sometimes we will write the notation for this if we have multiplicity as anytime there's a repeated, we'll put it in something that looks like an exponent but inside parentheses. So if you see something like this upstairs, it just means this is a repeated value and what you see inside is how often it's repeated. All right, so now we've done eigenvalues of J minus I, which gives us our complete graph.